Here's our team structure, with team leader being Cole Martin, propulsion leader Sergio Sanchez, design leader Ethan Liddell, system leader Blake Schlesinger, and the rest of us are there on the slides. All right, here's our mission profile. The VTOL aircraft is going to carry 4 passengers, pilot, and cargo. Our aircraft will be used for short routes in urban areas, designed for easy loading, unloading, quick takeoff, and landing by utilizing VTOL characteristics. By 2029, the aircraft will be outfitted with electric-powered thrust, but for now, we're going to do a hybrid system on the aircraft, and I'll explain more about that coming up. Here is our objectives: to make a compact aircraft, have more area than an ambulance for medical equipment, and have a range of at least 200 nautical miles, and decrease medical response times. Our goal is to be first company when a person is thinking about ordering an air taxi. We are determined to meet and surpass all of our key requirements. And here's our key requirements listed over here on the right side. Here's our benchmark data. As you can see, it's a small aircraft that we were benchmarking on many different characteristics such as payload range, propulsion systems, the Cessna 172, 162, Eclipse 500, SR-22, Beechcraft, and so on. The blue highlights do indicate our aircraft analysis. The benchmarking data is continued here. Here is the beginning of our trade studies. We had 6 different areas that we were focusing on, wing shape being one, propeller configuration being another. And as you can see here, the coaxial rotary type rotary wing aircraft here does not require a tail rotor, which was also part of our consideration. Here are the trade studies for the power plant and in the tail sections. And highlighted in yellow are the design criteria we went for. And you can see there's some noticeable differences in the overall point outcomes of the ones we were selected. Here's the trade study on the landing gear and the door placement. And with our design options, we include wing design, a high wing placement for greater accessibility, a slightly tapered medium aspect ratio is most efficient at our cruise speeds. Our plane will use low to medium cruise speeds, and the wings will account for much of the lift at higher speeds. Our propeller placement, as shown in the figure, we will have a coaxial rotary primary rotary wing design with a pusher prop on each wing, and that will be used primarily for higher cruise speeds. The the wing engines will be electric, and for the primary engine system for the rotors, we'll be using a conventional turbine engine.
Propulsion downselect involved a comparison of the multiple different engines seen in larger aircraft such as the Pavlo and Eurocopter X3. Each engine was compared based off its fuel capacity, weight, range, and complexity. The Rolls-Royce RTM Turbomeca engine was the best choice out of the other two internal combustion engines. Unlike most helicopters that are solely internal combustion, a hybrid solution was required. To fulfill this requirement, the YASA P400 electric motor was selected even though it received the worst rating. The reason behind this decision was due to the stackability of this motor. For example, 10 YASA P400 motors could be stacked to create the same power output of one Rolls-Royce engine. Similar helicopters like the Eurocopter X3 house two Turbomeca engines that spread the combined work across both the main prop and the pusher props. Since our helicopter is a hybrid, this would not be necessary since electric motors can carry some of that load. 10 YASA P400 motors power the dual pusher props on each wing, that's 5 on each side. All 10 motors operating at max RPM produce roughly 1600 kilowatts of power and weigh 240 kilograms in total. The main Turbomeca engine produces about 1611 kilowatts of power while weighing 232 kilograms. All of this power produced by the engine goes straight to the main props. When deciding how to integrate the propulsion systems, the primary goal was to make both types of power plants very accessible. The main internal combustion engine is located above the middle cabin, similar to most helicopters. At this location, it is seated directly under the main prop shaft with plenty of air that can be vented in from the top surface of the fuselage. Each pusher prop power plant consists of 5 YASA motors with a single shaft running through each. This assembly will be stored in the trailing edge of each delta wing with the fuel cells placed through the fuselage near the root of each wing. The thrust required/available curves for the pusher props display a maximum speed of approximately 200 miles per hour. This is an underestimation of the helicopter's performance since both the vertical and main props will aid in forward velocity. A max rate of climb can be achieved when the helicopter is climbing strictly vertical. At the maximum rate of climb of 8,000 feet per minute, the helicopter can reach its service ceiling of 12,000 feet in about a minute and a half.
Shown here is our 3-view graphic design with our side view, front view, and our isometric view. In the figures here, in our planform view, we show where our electric motor placement will be inside of our wings going horizontally across, as well as a storage unit just above it for placements of battery or fuel depending on our power source. Shown here in a little bit more detail for our fuel placements. On the left side we have our up close placement of our wing, which will hold either the battery or fuel. In this case it'll most likely be a battery for our hybrid propellers. And then on the right side we have our undercarriage fuel system, which will hold the majority of our fuel source, which will power the top propellers with our main engine. For a better idea of where all the placements are, here's a side view of what our design is looking to achieve. On the bottom of our aircraft we have our primary fuel reserve, which will be in our undercarriage, and then placed on the wing with the green dots will be our battery cell placement, which will be our hybrid implementation for our propellers. In order to place as much things as we're hoping for, such as the motors and battery, we will need a little bit more extra support in our wing, which is shown here with our ribs working their way horizontally across for a little more structure support.
We're now going to get into our performance estimates section, and you can see a list of the topics that are going to be covered in this section. Using the equations above, we were able to find the range and endurance for our aircraft, and you can see in the report a more detailed version of these. For the flight envelope, we first looked at X-foil to find the maximum coefficient of lift, which we found to be about 1.72, and then using equation 6.23, we were able to find the flight envelope, which can be seen on the right hand corner, and it is a measure of speed in knots versus load factor.
This is the structural analysis portion of our presentation, and below are the topics covered. So we'll be covering a material survey and selection, primary structural loads, structural design concept, landing gear design, and integration. So for our material survey and selection, we chose these 7 materials specifically because of their strengths, their densities, and their ability to withstand temperatures and shear forces for the craft. The metals we chose specifically because of their mechanical usages and the malleability of the metals in order to shape it into different sizes and shapes for the craft. The composites we chose for the same reason as the metals. They're similar in strength to the metals, if not equal to the strength, but they help us. They'll be able to help us cut down a lot on the weight of the overall craft. And polycarbonates have a good resistance to any natural corrosion that the craft can be exposed to. And below at the bottom of the slide, you'll see we have two tables showing you the strength, density, cost, and corrosive resistances of all the materials we have listed. So moving on to our primary structural loads. So we've calculated the wing loads to find regions of maximum stress along the span of the wing. And as expected, and as you can see here on these graphs over on the right side of the page, the wing loading moment becomes larger and larger as you move outward toward the wingtips. And all of our math was done and calculated using this Excel spreadsheet that we have here.